Okay, so I started doing the DeepMind RL lecture series. I've been wanting to get into RL for a while. I'm actually mainly into vision, so I'm quite new to all this. And actually, I've seen the Bellman equation. So this video is about the Bellman equation. I've seen that quite a few times when I've looked briefly into reinforcement learning in the past, and I've always found it that either the derivation of it is a bit hand wavy. So, this is a great lecture series, but I just found this derivation a bit short, and it wasn't clear to me how the steps are actually happening. Or I find that, I jump into Sutton and Bartow, and I jump to the relevant section, but I realize there's a lot I need to read before that to understand the context. So I just had to sit down and really, really think about it for a while and do everything really step by step and understand what's going on. Um, and I think I've achieved that. I'm recording this for myself for the future. And if you happen to pick this up as well, because you really want to understand what's going on deep down, you might find my explanation useful. And if you're a little more advanced, you can speed this video up. Um, but in any case, if you're watching this, I think that you should know what I mean when I say the Bellman equation, and you should know all the stuff that leads up to that. So I'm not going to go into explaining that, but I will recap it briefly at the start to try to make sure that we're all on the same page in terms of notation and what version of Markov decision processes we're talking about. Okay, so we're talking, actually I do need to change my screen. I haven't gotten used to editing yet, and I don't know if I want to. So this is going to stay in the video. Sorry. But now this should work. Excellent. So we have this idea of a Markov decision process where we have some state, use black, some state at some time, and then from that state we can take an action. And then by convention, that's also at time t. And based on that action, we receive jointly a reward at time t plus 1, again, based on convention, and a next state, time t plus 1. So these come together based on the action. And just to complete that, after that, we can do another action at time t plus 1, and that will give us a reward at time t plus 2, and a state at time t plus 3. And by the way, this state came together with a reward at time t, and that came from an action done at time t minus 1, and so on. So these states are all sets are all elements of the set of all possible states. The actions are all elements of the set of all possible actions, and the rewards. Let's just say here the reward can be any real number. And we have this other concept, which is the return. And the return, I had to clarify this to help me out, but the return is defined when you're in some state. So I'm going to write it here, and I'm going to write the return at time t plus 1 here. And the return is just the sum of all future rewards. And future means that we don't, so in the return at time t, we don't include the reward at time t, because that was already given with this state. And I'm talking about future rewards. So the return at time t is equal to the sum of all future rewards, like this, so on. But then you also have to, and again, I'll assume you know this coming to this video, so that you can apply a discount. And this is a discounted reward. So that's gamma squared. And one interesting question to ask is, given that I'm in a state, what is the sum of all future returns? And this is not easy. This is not easy because this chain of things or events here is not determined. It's probabilistic. And For the purpose of this, it's probabilistic in two ways. So one way is, given that I'm in state ST, or given that I'm in any state, the action that I choose is dependent on that state probabilistically. So you might start in some state, and there might be like 3 possible actions you could take. Just call A1, A2, A3, and each with some probability, 0.3, 0.4, whatever, right? And we can write that as, our policy. So this is a probability distribution, the probability of sum A given the state that we're in, right? And so that's to get from here to here. But then and we haven't even gotten to the first term in the series that we care about, because then after we do an action, we get a reward and a state based on that action. But again, that's not necessarily deterministic, and to be general, it's not deterministic. So that's also a probability distribution. Now it's a probability distribution over 2 possible variables, the reward and the S prime, I'll call it, which is the next state. It's just a prime because I've already got an S here, given the previous state and the action that you took. So on this tree of possible things to happen, this then comes out to be like you can fork out into all possible combinations of states and rewards. And actually, it's 2-dimensional distribution, so I won't even bother drawing it. And then, so you can see that just to get to the first reward in this series here, you already have to go through 2 probability distributions. And then to get to the next one after that, you have to go for 2 more, which depends on the outcome of the first 2. So you can see this tree expands pretty rapidly here. And it's hard to give a straightforward answer to the question, what is the return? But we know from probability theory that one useful thing that we like to think about is the expected value of a random variable. So we define this thing called a value function, depending on a state, and a policy. So under some policy, given that we're in some state, what is the expected return? And important here is we write this such that, or conditioned by, that the state at time t is equal to the little s here. So we can plug in some state, whatever state we want into this. And it's also, because we're considering the whole future as well, and we need to know all the actions that take place, it's also dependent on that policy, right? And now the idea with Bellman's equation is I need to be able to somehow write this value function recursively. So I need to write everything on the right-hand side as some expression involving, again, the value function, but maybe of some different state. And before I start stepping through that, really meticulously step by step, I want to just remind you that, I'll do it in purple here, that the expectation value of some random variable x, okay, so we have some random variable x under some probability distribution, p of x, right? And the expectation value, remember, is the sum over all x, p of x times x, right? And we're going to use that quite a lot here. So the bit that trips me up is the jump from the, there are like 2 steps I'm about to show you here. And what trips me up is it's shown in 1 step, because they expand this out twice, but they only do it in 1 line. And I'm going to expand it out twice, line by line right now. So remember, we only know the state we're in. Then there's this tree of possibilities which leads to the action. And then from that, there's a tree of possibilities for each branch of this tree that leads to the reward. And so it's hard to know what this reward is. But the first thing that we might do to simplify things for ourselves is pin down the action at least. So we can say, okay, well, there's all these possible actions that could come out of this state, but let's just consider them one by one. So we can do this in this summation. We can take a summation over all possible actions that we might take. And just like in this expansion here, we're going to look at the probability now of the action, which we're summing over, right, given the policy, because this is the probability distribution we have to look at when we're considering what's the action going to be. So that's why, actually this should be a pi then. Pi a given s, right? And then we've kind of pinned down a here because we can consider each term in this summation series one by one. So if we consider the first one, that's a1. We consider the second one, that's a2, etc. And now here, I'd like to be able to write, like in this expression, I'd like to just be able to write small g, but I can't because just because we've pinned down a, we still there's a branch, we branch out from a into all possible rewards and states because this is probabilistic too. By the way, actually, I'm just going to change this to, actually no, let's do, again, I would edit that out, but I can't be bothered. So anyway, so we can't do this. So this is still actually an expectation value. And this is the bit that tripped me up initially, but because it looks the same, and I've changed the expression, but now I've taken the expectation value inside. But this is a totally different expectation value. It's still an expectation value of the return. Let's see. I did miss a step here. I did miss a step. One more step here is that I can expand this out as the expectation value of and then we can write this out here. So what's the definition of GT? It's the reward at time t plus 1, right? Plus, and I'm not going to write out the rest of the series, it's gamma, the discount factor. And then if you look carefully, you can see that this is just GT plus 1, right? And then that's still conditioned on the state at time t being s and policy pi. And now we can go back to where I was just a few seconds ago, because now I'm going to do this. The expectation value of the sum is the sum of expectations, so I can do these one by one. So in green, I'm just going to consider this part of the sum. And this will get us back to where I was before I interrupted myself. So let's look at the expectation value of the reward at time step t plus 1, given the fact that we know that the state at time t is s, and we have policy pi. And again, we go through the same logic. I want to know this, and I have to pin down the action so I can look at the sum over all possible actions. And then this is this p term here, probability of that action given the state s. And now exactly where I was before, but now I say I can't just put r here, the reward, right? Because it's still unknown. Just because we've pinned down this action, we still don't know the reward because there's another probability distribution we need to get through to know it. So we still write down the expectation value here of the reward, given that the state is pinned down to be s. But now we don't need to say that we just know about the policy. We also have pinned down a, right? Because we're going through each step in this series sum, and we can consider what a is for each step. So we can say that the action at time t is a. This is the crucial bit for me that I missed when I was looking at all these derivations. And what confused me again was that we have an expectation value here of the same thing as here, but what's different is the conditions, right? And the fact that we've marginalized out a. So now the next step is to just look at this on its own. So I'm just going to copy this down, select it properly. Oops. Ugh, what a pain. I just have to write it again. Sum over all a pi a s. Now let's see if I can copy it. There we are. And now I'm going to expand out this expectation, because now I want to pin down the next bit, right? So I've pinned these two down, and now I want to pin down the next bit, and I can do this by summing over all the probability distribution for that. So again, I'm doing another expansion of this, a second expansion, using this template here, this purple template, and I'm doing the sum now. And because I've got two variables here, I'm doing the sum over r and the sum over s prime. Equivalently, I could have written sum over s prime, sum over r, and equivalently for notational convenience, I can just write r s prime like this under one summation. And then this is that probability distribution there, p r s prime, given that we know s, and we've also pinned down a, as I said before. And now we're allowed to just write r here. This is now allowed because we've pinned down everything we need to get from what we knew to start with to the reward that we're trying to find the expectation value of. So that's the first term, and as you can see here in this YouTube video, that's the first term here. Actually, no, this is the, here we go. This is the first term. So you've got that sum over pi, and then this probability distribution inside, and then r. So just in case you're following the DeepMind series as well. Now in blue, let's look at the next term here. Actually, I'm going to drop the gamma for now. We'll put it back in later. So now I'm just looking at the expectation value over the return at time t plus 1, given the state at time t was s, and we have policy pi. And what I don't like in some derivations, for me, it wasn't obvious why you were able to just substitute this for this here. Don't let that confuse you if you're not following this. But I can't just, my point is, just because of this definition here, I can't just replace this with that. Because this is a t plus 1, but in here we have it st. And here's a t and there's a t. You know, I don't know enough yet. I need to know what the state at time t plus 1 is in order to have this expression look exactly like this expression and be able to write, you know, something else, like to write this, right, as they do in the slide here. So I can't do that yet. And that's what tripped me up, and that's what I'm going through step by step now. So I can take the same steps as before. So the first thing, again, is I want to pin down the first action that happens after we're in the initial state that we're talking about. So we're going to sum over all possible actions, probability distribution of the actions given the state. And just as before, we can't just write G here, right? We actually have to write an expectation value again of G, so the return at time step t plus 1. And now this is conditioned on the state at time t is s, but now again we've relieved ourselves of the kind of uncertainty of what the next action is, because we've pinned it down outside here in the summation. And so the action at time t equals a, we pin that down. And then just as before, so again, we've pinned this down, we want to get to here, don't we? We want to get all the way over here this time, because that's the first term in GT. The first term in GT plus 1 is the reward at time t plus 2. So we've only pinned down these two. We need to pin the next thing down, which is these two. These two come about as a result of the action at time t. And so we do that the same way we did before, because we have a probability distribution for that. So rewrite the first part. Now we're going to expand this out according to, you know, the definition of an expectation value, and we're going to write out, just as we did before, sum over all rewards and s primes, probability of reward s prime given the existing the first state and the action that we've pinned down. And as before, I can't just write G here because I haven't pinned down enough things to get to, you know, to my R. So I still, again, have to write an expectation value over G. And again, I would have been really confused by this before, but remember, this looks the same as these, but the conditions are different. So the state at time t, now we know the state at time t plus 1 because we've pinned down the state at time t plus 1 to be S prime. And we've also, have we done? Yeah, we've pinned down the state at time t plus 1 to be S prime. Perfect. And is that all we need? And we also know what the policy is, by the way. I'm just going to add that in so you can see how the next step works. So the next step works like this. Now I'm allowed to do this substitution where this looks exactly like this, except now we have a t plus 1 and a t plus 1. So I can just copy this down. So let's see if I can get my copy to work. No. Why? I'm just going to right click on this. All right, I've done it. And now I can just write and now this is S prime by definition. So then I'm not going to write out the whole thing, but what we have is this basically. So we have the R from before, which we got. I think I see what's happened. I've accidentally disconnected my keyboard, which is why my key, I didn't realize it this whole time, but my keys weren't working. I did everything with a mouse. Okay. That's better. Again, I don't think I'm going to edit this out, but I fixed it. Sorry about that. So where were we? As I was saying, we have, if we sum that all together, we basically get this. So we get from the green bit, we get the R term here. And then from the blue bit, we get the gamma, because I took the gamma out, I have to put it back in, value function of S prime. And that's it. That's the Bellman equation, because now we've written the value function in terms of S, which referred to the state at time t. We've written that as a as some expression with now the value function at the next state. So that's the recursive bit. The next slide here, again, you don't have to be following this, but the next slide looks at the state action value. And again, I'll assume you know what this is. The state action value is kind of similar to the value function here, except the difference is this. So now we write Q pi S, and now we know we pin down the first action. So remember from this series here, we pin down the action at time t straight away from the outset, and that's equal to the expectation value. Again, same thing as before of the return, but now it's conditioned on the state at time t equals S and the action at time t equals A, and the policy, because we have all the future rewards to consider as well. And now is a good time, like if you think that this has helped you understand things more than you did before, this is a good time to then try to derive I'll put this link in my description at what's at 35 minutes here, which is this recursive relation for the Q value function, which looks a bit different. And I'm assuming you've paused now because I'm just going to blaze through it real quick. So again, we can rewrite this as the expectation value of the reward t plus 1 plus gamma reward t plus, well, I won't even write the expansion out. So that's gamma gt plus 1 given s of t equals s, a of t equals a at equals a pi. And then with green, I can just consider this part here. And then so with green, I'll write, okay, expectation value reward time t plus 1 sts ATA pi. And remember before we were saying, okay, we first need to pin down the action. So we do that by summing over all possible A using this probability distribution and this expansion for what the expectation value is. But now we don't need to do that because we've already pinned down A. So so remember how what the green bit looked like before? We did this first step where we expanded over all possible A. We can skip that step and we can jump straight to the second step where we, at least in order to get to the to this reward here, we need to pin down what comes out of this probability distribution. So we need to do this step. So basically that's the sum of all possible rewards and S primes, the next step you go into, of this probability distribution given S A. And we've pinned down A, it's here, so that's fine. And R, right? Because now R is determined. So that part's easy. And then for the blue, we'll do that as well. So that's expectation value. We'll skip the gamma. We'll put the gamma back in. The return time t plus 1, given we know that the state at time t is S, given that we know that the action at time t is A, and given our pi, our policy. And again, the first step is to do this expansion. To do the expansion that gets us from, we've pinned this down, we need to pin these two now. So that's this expansion here, S prime, SA. And now we have another expectation value inside here. It's again the expectation value of the return at time step t plus 1. But now we've pinned down to the next state, S prime. We still haven't pinned down the next action. So we still only know, considering this summation, we're not looking at the next action. So we still only know the first action, and then we know the policy. So what's the next step here? Because we still need to get to a place where we have an expression in here that looks like this. And so we have a gt plus 1, we have an st plus 1 equals s prime, but we still have an at, and that needs to be an at plus 1. And remember, we've pinned down we've obviously got the first state pinned down. We've pinned down the first action because that's by definition as well. We've just pinned down the reward and the next state. Now we need to pin down the next action. And the next action comes from this probability distribution. So we need to do this expansion here over that probability distribution. So now my keyboard is in range of the Bluetooth dongle, so I won't have issues. There we are. And then now we're going to sum over all possible actions given and now we can't use A because A is already in use. We are summing over all possible A primes, over all possible next actions. Probability distribution of A prime given the state that we're in, which is S prime now, because we've pinned that down too. And then now inside here, we have, again, an expectation value because we haven't pinned down everything we need to fully know what G is. So we still have an expectation value over G. But again, the conditions, that's the important bit, are different. So we've still got ST plus 1 equals S prime. Now we've got AT plus 1 equals A prime. And we've got pi. And now all of a sudden, this expression looks like the next version of this expression up here, because we have a plus 1 here and we have a prime here. So I can use my trusty copy paste again, and I can rewrite this bit as Q value function now of S prime A prime. And to save me from writing everything again, I'll just go back to these slides here. That's what you've got here. So you've got on the outside of the sum, you've got this, and then you've got the green bit to start with, the R right here.
This is the B that we've...
Oh, now you guys can tell I have Steam and I sometimes play games on my weekend. And and then where was I? Confused myself. Yeah, and then you have the q value function. And another thing that bamboozled me before I fully understood what was going on is like why these two look so different. Because here you don't have that first summation over all possible actions. And now I fully understand why that's the case, is because we've pinned down the first possible action. We don't need to sum over all possible actions because we know what the action is. And then we have a summation over the next possible action inside the sum for the q value function, but not for the v value for the value function. And that's because the value function doesn't require us to know what the next action is. Whereas the state action value, I also know about the q value. I think it's also called the q value. That's why I keep mixing up my terms. But this one requires us to pin down that a. So that's why we have to go all the way to pinning down the a before we can do that substitution here. So you kind of, where you pin down the a on one end, so you lose that complication here. You end up adding more complication on the other end of things because you've unpinned, or you have to then go to the work of pinning down the next action. Wow, that was a mouthful, or lots of mouthfuls. That was hard to explain, hard to get through, but it's certainly going to be helpful for me, like, because I'm going to forget this again for sure. I'm going to look at the Bellman equation, unless I stick to RL and do it all the time, which I'm not necessarily going to do. This is just like a side thing for me. I'm going to forget, but if I look at this video again, I'll certainly remember and understand. And I hope if you've made it this far and you found this interesting, you can have this as something that you can look back on if you need to. Thanks.